Imagine a battlefield where ammunition is virtually limitless, where precision strikes move at the speed of light, and where the clash of conventional arms gives way to beams of pure energy. This is not a distant fantasy, but the emerging reality of directed energy weapons, particularly high-energy lasers, poised to redefine military capabilities worldwide. These sophisticated technologies are rapidly maturing, becoming more efficient, more compact, and increasingly integral to modern defense strategies. Directed energy weapons encompass a range of technologies, with high-energy lasers forming a crucial subset. While the concept may sound like something from science fiction, militaries across the globe are heavily investing in their development and deployment. Lasers have, in fact, been utilized by armed forces for a considerable period, primarily for tasks such as range-finding or guiding precision munitions to their targets. What is fundamentally new, however, is their evolution into active offensive and defensive systems. This new class of lasers harnesses electrical energy, which is fed into specialized materials to generate photons, light particles, that are then focused into an intense, coherent beam. This beam is directed at a target, and the resulting effects can vary based on power and intended use, ranging from disabling to destructive. For instance, a laser could effectively burn a hole through the wing of an unmanned aerial vehicle, UAV, or other specific targets. The operational benefits of such systems are compelling. Foremost among them is speed. A laser beam travels literally at the speed of light, making engagement times incredibly swift. While an instantaneous effect is not always guaranteed, it might require a second or two of sustained focus on target. The rapid initial engagement and subsequent retargeting capabilities are unmatched. Line of sight is a fundamental limitation, as light travels in straight lines, preventing over-the-horizon engagements. However, within the horizon, targets can be engaged and neutralized with remarkable speed, and then the system can swiftly move to the next threat. Crucially, this can be achieved at an extraordinarily low cost per shot. In various conflicts, expensive interceptor missiles, such as the high-end air defense missiles designed to counter fast-moving, high-altitude threats, can cost hundreds of thousands or even millions of pounds. In stark contrast, a laser shot can reportedly cost as little as 10 to 20 pounds, offering a radical reduction in operational expenditure. Another significant advantage frequently cited is the concept of an infinite magazine. Traditional kinetic weapons, like bullets or missiles, have a finite supply of ammunition, and once depleted, the system is rendered ineffective. With laser weapons, the theoretical idea is that as long as they are connected to an electrical power source, they can continue firing. While not truly infinite, systems can deplete their electrical power. This capability vastly extends engagement capacity compared to conventional munitions, providing significantly more shots before needing to resupply. However, these revolutionary capabilities come with their own set of significant challenges. One of the primary concerns is thermal management. High-energy lasers typically convert only about 50% of their electrical power into the directed energy beam. The remaining 50% is converted into heat. For a powerful 100 kilowatt laser, this means dealing with an immense 50 kilowatts of waste heat, demanding sophisticated cooling systems to prevent overheating and ensure sustained operation. Environmental factors also pose considerable limitations. Laser beams can be diminished, altered, and degraded by various atmospheric effects. Even on a clear day, atmospheric turbulence can cause distortions. More significantly, adverse weather conditions such as rain, snow, mist, or fog can severely degrade a laser beam's effectiveness. Furthermore, the chaotic environment of a battlefield, replete with explosions, smoke, and dust, can significantly reduce the performance of laser systems. Another critical challenge in deploying laser weapon systems pertains to collateral damage and deconfliction. A high-power laser beam fired into the sky can travel for many kilometers. If aimed at a drone, for example, and the target is missed, the beam's trajectory beyond the target becomes a concern. Similarly, reflected laser light from surfaces of the target or other objects could pose a hazard. A major concern in this context is the potential for blinding individuals or damaging eyesight, even from indirect or reflected laser exposure. The vision of multiple laser beams crisscrossing the sky, while technologically possible, underscores the need to meticulously account for these unintended side effects to ensure responsible and safe deployment. Despite these challenges, nations are actively pursuing the integration of laser technology into their defense architectures. One notable example is the deployment of layered air defense systems to protect both military installations and civilian populations. While existing missile-based systems, such as the renowned Iron Dome, have proven highly effective, the sheer volume of incoming aerial threats, including missiles and drones, constrain stockpiles of interceptor missiles and incur massive costs for sustained operations. Recent conflicts have demonstrated the financial burden of high-tempo air defense, even when highly successful. This is where advanced laser systems, such as Iron Beam, come into play. While not a singular, silver bullet solution, they provide an additional, cost-effective layer to existing defenses. Their effective ranges and power levels are particularly well suited for countering relatively short-range rockets and missiles. A 100 kilowatt laser, sustained on target for sufficient time, can reliably disable incoming threats. A nation's proficiency in integrating lasers into comprehensive air defense systems, protecting against a spectrum of missiles, rockets, and drones, appears to be a leading example globally. Such advancements are crucial for maintaining defense capabilities in an evolving threat landscape. The situation in other conflict zones highlights a similar necessity for such technologies. Drone warfare has become increasingly prevalent and effective for both sides in certain conflicts, making the desire for capabilities like an infinite magazine understandable. If directed energy weapons are deployed en masse, they could have a significant tactical impact, leading to strategic implications. Currently, defenders often face overwhelming saturation attacks, where the sheer number of incoming threats, whether targeting military objectives or civilian areas, can overwhelm conventional defenses. This creates an inherent tactical advantage for the offense. However, the introduction of advanced defensive systems like directed energy weapons could potentially shift this balance back towards the defender, offering new means to protect military forces and civilian populations, and mitigating the threat posed by drones and other aerial munitions. This dynamic will undoubtedly continue to evolve with the development of countermeasures and countermeasures, but at the tactical level, it holds the potential to significantly alter the offense-defense equilibrium. Beyond their destructive applications, lasers have long been utilized for non-lethal purposes, specifically, dazzling. This involves shining a laser into an opponent's sensor to blind or degrade its functionality. Such systems are already deployed on large aircraft to defeat heat-seeking missiles by blinding their guidance sensors. The same principle can be applied to satellites. Military satellites, in particular, are vital for Earth observation, and while physically destroying them carries significant diplomatic repercussions, dazzling their sensors from the ground offers a way to degrade their capabilities without destruction. This requires a high-energy laser due to the vast distances involved and introduces a critical diplomatic dimension to the use of lasers against spacecraft. Looking further ahead, the future battlefield will likely be shaped by the convergence of multiple advanced technologies. Alongside directed energy weapons, artificial intelligence, AI, and increasing autonomy will play a transformative role. Many drones today are still remotely piloted, but future automation and autonomous capabilities could dramatically alter their effectiveness. Quantum technologies also hold the potential to revolutionize battlefield sensing, computing power, and decision-making capabilities, enabling forces to anticipate adversaries with greater precision. Other advanced weapons, such as hypersonics and novel space or cyber capabilities, will further contribute to this complex interplay. The ultimate advantage will lie not just in developing these individual technologies, but in how effectively they are combined, who devises the most innovative tactics for their use, and which industrial bases can produce them at scale. Certain nations are actively positioning themselves at the forefront of this technological evolution. Successful testing of prototypes has been observed, and strategic defense reviews have emphasized the development of advantages in various technology areas, with directed energy weapons specifically identified as a key focus. These systems are viewed not only as a means to fill urgent capability gaps in national defense, such as protecting airspace, but also as a way to support allies. This could involve forward deploying systems to strategic locations or potentially providing them to nations facing significant aerial threats. This suggests a strong national position, bolstered by considerable expertise from defense science and technology laboratories and a consortium of companies involved in developing these weapons. A crucial challenge, however, lies in overcoming the valley of death, the notorious gap between innovative research and actual military deployment. Many countries excel at developing brilliant ideas, but translating them into deployed, commercialized, and operational military assets often falters due to bureaucracy, extensive testing, and production hurdles. The current imperative is to accelerate this procurement process significantly faster than in previous decades. The future will undoubtedly see laser weapons becoming more efficient and compact. Small vehicles, ships, and even aircraft are being designed to integrate these systems. Concurrently, the development of robots and autonomous systems continues to advance, albeit with some developmental challenges, much like autonomous vehicles for civilian use. While a future with fewer human combatants and more robots seems plausible, particularly when looking far enough ahead, it is vital that this transition is managed with extreme care. Key decisions in warfare, especially those involving the use of lethal force, should arguably always remain within human oversight and control. There is significant interest in miniaturizing directed energy technology, and future combat aircraft are being designed with this in mind. For example, the Global Combat Air Program, GCAP, involving several nations, is developing a new combat aircraft designed to be larger than current models. This size provides not only greater payload capacity for fuel and conventional munitions but also crucial space and power management systems to integrate future sensors, advanced computing, and energy-intensive systems like lasers. This proactive design ensures that the aircraft can be upgraded with emerging technologies rather than being physically constrained. The same forward-thinking approach is being applied to ground vehicles, where there is interest in enhancing tank defenses with miniaturized laser or radio frequency active protection systems against incoming threats. As these weapons become smaller, they will proliferate, increasing both their numbers on the battlefield and the variety of platforms on which they are employed. Space will also become an increasingly important domain for directed energy applications. Beyond existing ground-to-space laser targeting for satellites, future scenarios could involve space-based systems countering other co-orbital threats. While this evokes dramatic visions of space combat from popular culture, the reality will likely be less theatrical, focusing on precise, strategic engagements rather than spectacular visual effects. In conclusion, the maturation of directed energy weapons, particularly high-energy lasers, marks a profound shift in military capabilities. Offering unparalleled speed, cost-effectiveness, and extended engagement capacity, these systems promise to enhance defensive postures and potentially rebalance the offense-defense dynamic in modern warfare. While significant challenges related to thermal management, environmental interference, and the ethical implications of collateral damage remain, ongoing advancements in miniaturization and integration with other cutting-edge technologies like AI and autonomy are driving their relentless progression. The strategic deployment of these formidable tools, coupled with a commitment to human oversight and responsible development, will be paramount as we navigate this increasingly technological and complex future of conflict.